it's facing backwards. It hangs over the ear and comes down. Ah, okay.
Everybody hear me?
I can hear you.
All right, let's get started then.
All right.
So I'm going to talk a little about Reactive I/O with Akka, Play, and Scala. So when we say reactive, we're not really strictly talking about reactive functional programming, obviously. What we're really talking about is the ability to deal with throughput, latency, application errors, and network failures. The reason this is important for what I do at least is because primarily my servers aren't compute bound at all, right? I mean, I run cycles maybe 10-15% of CPU utilization. Where I am bound is throughput, both with respect to network and disk. And if I write my code effectively, I'm able to minimize the CPU utilization and still provide a good quality of service to clients of the services that I stand up in the back office. Now, also, we generally want to use I/O-bound code, meaning code that's reading from a network or writing to a file, and integrate it in a concurrent pipeline with code that's actually executing business logic on the code. And we want to do this in a manner that doesn't block. So we don't want to explicitly call a mutex. We don't want to explicitly lock on something. We don't want to explicitly wait for something to complete. We want to stage our computation such that it's just a pipe of incoming data that performs some transformations and then outputs. And for us at least, the type-safe stack, Scala, Akka, and Play has been a really good enabler to move away from traditional like J2EE models and traditional Java concurrency primitives into a world where, you know, when you're using a future instead of just immediately creating a future, calling get and blocking, you can construct monadic computation by mapping the future with some transformation and just structure the code that way. So the reason we use Scala is because we're a core JVM shop, right? Now, as much as I'd love to use Haskell, as much as I'd love to use Erlang, the guys in my shop are really good at tuning the JVM in production environments to be performant. So while it is ultimately by decision, I can go ahead and use Erlang, I'm not going to get a whole lot of support from my team in terms of being able to launch the application, deploy the application at scale, and then make sure it's functioning in a production environment. And the other reason is that we do have a lot of people who are coming from procedural and OO worlds, right? So, I mean, I like to say that a good Java developer can already write some bad Scala, right? And the other thing is the type-safe stack really does scale. I mean, the location transparency of actors, the clustering utilities, and the fault tolerance that it provides have allowed us to build very large systems in a production environment relatively rapidly. So just about the techniques that we tend to use. I already spoke a little bit about promises and futures. So effectively, a promise is just a single assignment variable that sets the value of a future. A future, at some point, will be completed by that promise and allow computation to continue. As I already said, the benefit is that they're monads. So we can chain asynchronous processes together, and the code executes when the future, well, the promise completes and the future becomes available. The problems we face are that these type of pipelines aren't particularly good at encapsulating mutable state, meaning that sometimes immature developers have a tendency to do things like close over a mutable variable that's not actually available in the scope of the context of the future that's executing. So for those of you from the Haskell world, I'm sure you're familiar with iteratives, which were basically designed to kind of get around this, to allow some type of mutable state that, well, to allow you to encapsulate mutable state in the context of asynchronous processing. And basically, an iterative just folds a step, where a step is either done, continued, and in the Scala case error, Haskell is a slightly different semantic, but effectively the same thing. Enumerators just provide data to iteratives. And an enumerative, it's a functional transform that maps iteratives to other iteratives, or maps enumerators to other enumerators. Now, it allows for event-driven code using pure functional programming. which is very nice. It allows you to not have to worry too much about mutable state. And the play library provides a large range of pre-built functions that allow you to do kind of nifty things with iteratives and enumerators, which we'll get into later. But they're still not particularly great for handling error conditions, right? They don't provide any type of supervision. So when your enumerative fails, you get an error, but what do you do with that error? How do you restructure your computation to deal with that error situation? It's really not a clear-cut path to do that. So then the other thing we use are actors. And actors, at least from my first experience, were from Erlang, right? So, I mean, they're also a theoretic construct used to make formal proofs about communicating sequential processes, but in practice, they're a primitive for asynchronous computation, right? So they can send a finite number of messages, spawn a finite number of children, and they can modify their behavior, meaning modify the semantics of their execution when triggered by another message. Actor systems just basically aggregate a set of, well, really more a hierarchy of actors into a program executing the business logic that you want. So they're really great for encapsulating mutable state, and they allow for easy specification of recovery strategies, but they're not particularly type safe, meaning that inside the body of an actor, you implement a single function as necessity, which is receive, which effectively takes anything and produces nothing. So there's really no good way to specify that, okay, this actor should take only values of this type and return only values of this type, to specify a domain and a range. And also, they're not particularly composable. While they can be composed, there's no type safety in the composition of an actor, or of two actors. So I'm going to walk through a little example of the type of thing we do. This is not actually the production code that we use, but it's a good example of the types of libraries that we write. So generally, we have multiple tiers in an application. The presentation tier might do something like present HTML, or some other content over HTTP, or communicate with the client over WebSockets. Typically, that would be fronted by some type of a load balancer, either software or hardware. And then, usually those applications will go back and communicate with the backend service. Now, a backend service, we generally are not going to use HTTP. Just because it's a request-reply model that allows one outstanding request with one outstanding reply, and even the performance when pipeline are using Speedy isn't as good as using a terse binary format. So a little bit of, let me see if I can pull this up.
Like that, the plus, or? That's a little bit better. So for this notional DB service, where we're going to support get, put, and delete, this is a play controller. And it's relatively straightforward. It's just basically taking an action which takes an implicit request and produces a result. The result is generally an HTTP response, and the request is an HTTP request. So assuming we have a client that implements communication to the backend server efficiently, we can relatively rapidly prototype the front-end service. All you have to do is implement get, decodes the base64 key contained in the request body, or I'm sorry, either as a query string parameter or as an appending to a dynamic URL. Calls the client for the backend service, retrieves the key, creates a response, and then recovers with an error result. And an error result is just basically taking a throwable, extracting the message, and constructing a JSON object. Put, delete basically work the same. WebSockets is a little bit more interesting in that you're either forced to use an actor or forced to use an iterative. Actually, a combination of an iterative and enumerator. So we implement this by creating a channel. So a channel is an enumerator that allows me to push a response into a directory. Because the channel isn't actually going to exist until I pass it into the infrastructure itself, I have to create the channel as a promise. And the response enumerator is a unicast enumerator that I'm going to use to broadcast the responses. So when I return this enumerator that's mapping a JS value into a collection of optional requests, if parsing fails, then nothing is generated. I take the request, I use the iterative, which I'm flattening the future of the actual promise of the iterative, and then mapping the response into JSON. And then the actual business logic is as simple as this response enum right here. All I'm doing is taking the response for each request, sending it to the client, mapping the response back out, and pushing it to JSON. So it pretty much lets me do the entire WebSocket library in like, I don't know, what's that, like 50, 60 lines of code. Okay, let me go a little bit faster.
These times on the side.
Well, I think we start at 25 minutes, that's my point.
Yeah.
Okay, so moving on, what we really want to do is be able to generate a generic protocol that implements back pressure to prevent the server from being knocked over. And what do we mean by that? So with TCP, what you generally want to do, any protocol that's riding TCP, in the event that you're getting too much data in, you want to suspend reading from the socket, force the back pressure onto the client, right? Meaning that when you stop reading, it fills up your TCP buffer, the client's TCP buffer fills up, and it can no longer write it. So you're going to force that pressure back onto the client. Now, we generally do this by hysteresis, and hysteresis just basically means I'm going to wait until I have X number of bytes in my buffer, right? At this point, I'm going to say, okay, I can't take anymore. I'm at a high water mark. So I'm going to stop reading. I'm going to serve off requests into an individual service. Then I'm going to resume reading when I hit my low water mark. We do the same thing with accepting connections. Now, if you wanted to do this out of the box, you could use something like Finagle for request reply model. The places that it fails, and the reason that we weren't able to use it in all instances, is that the intuition of how it operates is based primarily upon the idea that all work is being generated from a request into the server, right? So if you have a truly asynchronous protocol where the server is calling back to the client, it's unclear that hysteresis is optimal, and you may actually balance between states where the client blocks the server blocks the client. So we ended up writing our own abstract IO libraries in order to deal with these situations. But what I'm going to present is a request reply model fundamentally, but it's not necessarily just in that niche. So in effect, what we do is we first have to deal with the Akka TCP libraries. Now, they're much better than the native NIO libraries in terms of they have already an actor-based syntax for implementing the reactor to deal with the NIO selector, which is the fundamental primitive that you're using to determine when IO is ready on a file descriptor. But they don't buffer for you. So the tricky part is writing optimistically until you fail a write, then buffering requests until you can resume writing again. You can also do this act-based, as in, I'm going to send a write, wait till the operating system receives it, wait till it acknowledges it back. But you get about 10,000 requests per second on host if you do it that way. So it's rather important to use optimistic write through in order to get good performance out of it. And we implemented it basically as a finite state machine. So you start off in a state where you're optimistically writing. In the event that you get a write fail, you go to buffering. When writing resumes, you transition back to optimistic, stopping along the way in a state where you are acknowledging, because you don't want to throttle between buffering and optimistic writing. And all in all, the actual code, because Akka supports finite state machines, is relatively simple. You just declare an FSM with the particular states of interest. For each event, you deal with it. First one's writing, then acting. You see the command failed, transitions to buffering. And all the states pretty much look like that.
But what we'd really like to do is wrap up logic like that instead of an abstract protocol that takes a request, a response, and an ID correlating the request and the response. Defines the message size bounding, the byte order rate, how messages are marshaled and unmarshaled, the protocol framing, and by that I mean something, maybe you're using a length field prefix, maybe you're using a string delimiter or whatever. And we want to define the back pressure model and hysteresis parameters, along with the TCP buffer size, because if the buffer does overflow, we're forced to disconnect it. We also want to define the client with client routing logic. So for our DB example, it doesn't make sense to round robin between backend servers. You have to make sure that the individual key that you're using goes to a particular server or set thereof. So we want to be able to abstractly say that I want to use consistent hashing for the client, and that's how it's going to communicate with the server. Encapsulate that in the protocol so that both client and server agree on it prior to compilation. And that pretty much looks like this. So in effect, we just define a type trait that's going to be a protocol, and that our abstract client and abstract server can actually just inherit as an implicit parameter and then go forward. So the server itself basically just takes a service, which implements, well, takes a function from request to response, and executes it inside the framework of an actor. The reason we do it inside of an actor body is so that any error messages that are specific to the domain can be handled by the supervisor strategy specified. Meaning that if I have time to show the example, if you have a database exception, for instance, and you don't want to shut down the first occurrence, you want to shut down if you get 20 after 10 minutes, it allows you to specify that logic. Shared service, which we're using, basically allows multiple connections to use a single actor, multiplexing requests to that actor. So by default, when you create a connection, it's going to create its own service actor that executes this method. Shared service allows all of the connections to use the same actor. For the DB, this becomes relatively important. And then the connection actor basically just implements a logic that we talked about previously. It starts at active. If the number of requests that are currently outstanding to the service actor exceeds a high water mark, it just stops reading, goes to suspended. In the event the client closes, it'll continue pushing stuff through and until all the requests are served and then shut down. The acceptor has a similar hysteresis behavior, but with respect to the number of incoming connections. And the client basically does the reverse of it. It tracks everything via a transaction. So a transaction just basically takes... Transaction basically aggregates a request to a function that's complete if a response is available, and a function that occurs if an error is available. From that basis, we can use a promise, for instance, to just construct one that's used purely asynchronously and promise future model. And we can also construct one that'll send a response to an actor or send a request failed to an actor. So the transaction model integrates well with all three paradigms that we use. And at the end, the client basically just can be used as an actor reference. You can tell it a message. You can use request, future response, so on and so on. So the end goal of it is ultimately to be able to write code like this. So instead of having to do a whole bunch of configuration, write a whole bunch of classes, do a whole bunch of inheritance, I can just use my abstract protocol, import the protocol that I want, load the configuration parameters for hysteresis and for back pressure directly from the configuration file, and run. The DB protocol is relatively simple to write. Just a bunch of status codes, and then indication of request and response types, default parameters for how it's going to behave in terms of dealing with back pressure, basic byte string serialization and deserialization, defining that the routing logic should be consistent hashing, and I can override this with round robin or random, and then actually implementing the service itself, which is as simple as opening a file, taking in an individual request, and executing it. And then when I want to integrate the client side, it's basically just a bunch of wrappers around the existing client. I mean, this is all the logic I need to stand up the other side of it. So the idea is to drastically reduce the amount of templated boilerplate code that you need in order to implement back pressure, but to do it intelligently, and to be able to rapidly design services using that infrastructure. I'll go with any. Any questions?
Thank you. We have time for pretty much one question, I think, at this point.
No question.
Hoping to use that to cover the transfer. Hello. We get to end our day.